Good. So this session is entirely about quadratics. You probably first learned about quadratics when you were maybe 8 years old, and it got you excited about math. And you probably thought as an 8-year-old that you could do quadratics for the rest of your life and get paid for it. Well, in fact, you can, and this session will prove that. So the first talk is by Gonzalo Muñoz, Maximal Quadratic-Free Sets.
Thank you, John. So can you see my pointer just fine? Yeah? Okay, great. So, so this work that I'm presenting is joint work with Felipe Serrano from ZIB, and I recently moved back to Chile to this brand new university, Universidad de O'Higgins is the name, and I hold an academic position here. So let's get down to business. So the motivation of our constructions, let's say, of these maximal quadratic free sets that I will define in a second, comes from intersection cuts, okay? So intersection cuts, it's probably very familiar to many of you, but I'm going to introduce them with a few pictures just in case you haven't seen them. So the idea is the following. Suppose that you want to optimize over this, this blue region, okay, which is non-convex, and then using some LP-based method, you get a relaxation and you get this black point right here. So you want to separate that point from the blue region. So what you can do, and what intersection cut paradigm does, is you can construct what we call an S-free set. So it's a convex set that does not intersect your region of interest, which in this case is the blue one. And what you do is you just look at the intersection of these rays, and what these rays are just rays of a conic relaxation of your set, okay, which is again the blue set. And you look at these intersection points here, and then you construct just a hyperplane that goes through them, hence the name intersection cut. This was introduced by Balas, although these type of cuts were used before by TUI in this concavity cuts by TUI. But then when they were introduced by Balas, they have been largely studied in the integer programming community. Now, a few things to keep in mind besides this very nice geometric construction is the following. If you have a larger S-free set, that's better in general. So in this case, you can see that you can have this purple S-free set, which is larger than the green one. And then if you look at the intersection points of this purple set, you get a better cut. Okay, in this case, it's a very deep cut. You don't know how deep it's going to be in general, but it's going to be better if the set is bigger. That's the idea to keep in mind. So we define the notion of maximality in this sense, in the inclusion-wise sense. So we're going to say that a set C is maximal S-free if it's not contained in any other S-free set. Okay, so that's the definition to keep in mind. So one important case that we're going to deal with, which is what John was mentioning at the beginning of the session, is the quadratic set. So what we're going to work with here is a set that is defined using just one quadratic. Okay, so just one general quadratic inequality that can be, well, we're actually going to assume that it's non-convex. Okay, to make things a bit more interesting. And we're going to assume that we have a point X bar that you want to separate from this region. Now, a few things to keep in mind here. Even though I'm only considering one quadratic constraint, this doesn't mean that it only applies to problems with only one quadratic constraints. Because if you have let's say an LP-based solution method, you construct you have a vertex. And even if your original problem has many quadratic constraints, well, there's one that's going to be violated. This is what we're assuming. So we're going to focus on that one. Okay, so you can apply. It's just that you're going to look at one at a time. And this is what I'm just saying here, that if X bar does not belong to an intersection of quadratics, there's one that is violated. And another thing to keep in mind is that normally when you construct this cone that I showed at the beginning, that it's also carrying information of the rest of the problem. Okay, so the cut that you would get will also have that information. Okay, it's just that in our case the maximality notion of our sets is going to be with respect to this one quadratic set. Okay. So for the rest of the talk, what I'm going to do is show you how we can obtain maximal quadratic-free sets. So convex set that will contain a point of interest and that will be maximal with respect to this quadratic set that is defined with one quadratic inequality. So the outline of what it's coming up, at the beginning I'm going to show you how we can actually prove maximality, okay, because this is something that that is known for lattice-free sets when you want to do a maximal lattice-free set, that we generalize part of that to this quadratic-free sets. Well, we actually did it for a general case, but we're applying it for the quadratic-free sets. Then I'm going to show you how to handle homogeneous quadratics. Then we're going to have to take an intermediate step that we're going to add a single constraint to a set that I'm going to describe in a second. Well, not in a second, in a few minutes. And then we're going to move to non-homogeneous quadratic, which is the hard case, okay? So if there's any questions, I think you can just write them in the chat. So let's go with the first question. How do we actually prove maximality in this case where you don't have a lattice and you have just this quadratic set or any closed set? So let's look at the integer programming case and what's the criteria for maximality in the integer programming set. So you have your lattice with this black dots, and then you have this S-free set that is the green one. The other things, don't worry, I just put them there to give you some context, but we're actually just worried about the green set in this case. So this set right here is not maximal, right? So you can enlarge it a little bit more. Now, if you enlarge it, this one is maximal, right? So let me just go back and forth so the idea sticks. And what's the big difference between this one and this one? How you can actually certify that the second one is maximal, that you can just not grow it anymore. And the key point here is that the large one, it's a polyhedron, and if I look at each one of the facets of that polyhedron, there is one of my points of interest of my lattice in the relative interior of that facet. That's the key. In this one, that doesn't happen. There is this facet that, since it doesn't have a point there, that I can sort of make it a little bit larger in that direction. This one, I cannot. This one, I just cannot push on any direction to make it larger. So this idea is what we're going to recycle for our quadratic-free sets, well, and actually for any closed set S. And since in general we don't necessarily have facets, we're going to have to make the definition a little bit different, but the spirit is the same, okay? So what we're going to do is define an exposing point for an inequality. So we're going to have take a convex set C, a valid inequality for that convex set, which I'm going to term A transpose and beta. And I'm going to say that a point x0 will expose this inequality if the inequality is tight at x0, and that inequality is the only tight inequality in that point. So for example, let me give you an example here. Take the convex set, this ball, this green ball here, and take this purple valid inequality. Okay, so this valid inequality is exposed by a point here right here in the tangent point, because that point is tight for this inequality, or well, the inequality is tight at that point, right? And that is actually the only valid tight inequality at that point. So what this point is doing is exposing this inequality. Okay. And the idea is that with this, we're going to be able to generalize this, point being in the relative interior of a facet. Okay, so what do we prove with this notion of exposing point? So what we prove is the following. Take a convex set and take an outer description of that convex set. So this is what I write here. So just take a convex set defined by some set of linear inequalities. This set, of course, doesn't have to be finite. It can be anything. But now suppose that all this set of inequalities, each one of them has an exposing point in the intersection of the set and your set of interest, sorry, the S-free set, C, and in the set of interest, S. Then you have that C, you can prove that then C is going to be maximal S-free. So let's go back to the example of the ball. In the ball now I drew a bunch of valid linear inequalities. And now think of S as the complement, as the orange part, okay? So how can I certify that C is maximal S-free with respect to this orange region? I can look at each one of these valid linear inequalities. I look at the exposing point, or I search for an exposing point of that inequality that is in the intersection of S, the orange region, and C, the green region. If I can do that for all the inequalities, then it's maximal S-free. Okay, and this is only a sufficient condition, by the way. We still haven't been able to crack the necessary condition in this general case, but this is a generalization of the sufficient part of this lattice-free criteria. Okay, if you apply this to lattice to S, when S is a lattice, you get the criteria of Day and Woolsey. Okay, so now let's use this criteria to prove maximality for quadratic sets. So the first one that we're going to do is homogeneous quadratics. So take a quadratic that looks like this, only has the quadratic part. This is the assumption that it's homogeneous. Now the first step that we do is bring this to this form. This is via diagonalization. Okay, this is something that actually Shantanu discussed also in his course for the summer school. He also used this form, or the square of it. So you can always transform this via a linear one-to-one transformation into this. Don't be scared by the norms. They can also be square norms. It's just that we use an equivalent description. But the transformation of variables is linear and one-to-one. It's just a diagonalization. Now, once you transform this via a linear one-to-one transformation, maximality and S-freeness carries over. And that's very important. So now I can just work on this set. And if I construct something maximal for this set, I can construct something back for the original set. So this set in 3D, it's a little bit limited, but it's still gonna be helpful to show our results. So in 3D, it's just this hourglass or the complement of it. So let's construct maximal S-free sets for this. Now, it is not too hard to prove that this set C lambda that I'm defining here, so I kept the norm of Y. Let me just show you the set before here. It's norm of X less or equal the norm of Y. That's the set, the set S. Now, I have the norm of Y here, and I have it upper bounded by lambda transpose X. So if you upper bound this using Cauchy-Schwarz, you get the complement of the other set. You get the norm here, and which is the reverse inequality of the other one. So this is not hard to see that is actually S-free. Okay, and if you pick the right lambda, it will contain the point that you want in the interior. If you choose this lambda, you're good. You have an S-free set that has this point in the interior. Maximality is what you need to prove, and it's actually not too bad in this case. And let me show you the proof first by pictures. In this case, the sets that we get, the set C lambda, I draw it in, we plot it in green. And you can see that it's sort of either this wedge going into the hourglass, or is one of these convex cones in either side of the complement of the hourglass. So, and you can see that the criteria here works, because if you look at this facet in this case, it does have exposing points in the intersection of both. And the same thing happens here, okay? That's how the criteria works. So let's write that with math. So I can write the description of this set C lambda, of the green set. I can use another description in this form. So you can just take all the subgradients of the norm function. And you get this subgradient, so you get a family of inequalities parametrized by this beta, which is just a beta in the unit ball. Okay, so each point in the unit ball will give you a valid inequality that you just sort of go around. And now you have this outer description of your set. And then what you can do is look for an exposing point for each one of these inequalities. And we show that the point lambda beta, it's actually part of, the exposing point that you want. It's in the intersection of both and exposes the inequality that you want. And that's the proof. So now we want to work toward non-homogeneous quadratics. So the intermediate step that we're going to do is include a linear constraint. And how am I going to do that? So any quadratic, when it's, I should say any non-homogeneous quadratic here, can be brought to this form. Because I can, before I did a diagonalization, on top of that I can do a homogenization, okay? And what a homogenization does is it lifts your set to one more dimension, and then it cuts it with a linear equality, sorry. And that you can write it in general terms like this. You can just write the same inequality that I had before, and then a linear equality in order to recover your quadratic set. As long as it's non-homogeneous, you can always do this. Now, as an intermediate step, I'm going to relax this constraint of equal to -1. This -1 is not important. It could have been just 1. It doesn't really matter. But I'm going to relax it to less or equal than 0. Okay, this is going to be the first step, the first construction. And now it turns out that in this case, the things start to get more complicated, and we need two different constructions depending on the norm of this coefficients of A and D. It sort of depends on how you're actually cutting through the quadratic, on how you build the quadratic-free set. So let's go to the first case. So what happened with C lambda, the set that I had before, this either the wedge or one of the parts of the complement of the hourglass. So in this case, you have in orange, we have the complement of the hourglass, and now I sliced it with an inequality. So you can see here that the set that I had before is no longer maximal. Okay, and there's a problem here because all of this area here, all of this region here, sort of lost. These points are no longer exposing points. They used to be exposing points here, but now they're not anymore. And that's the issue. And how do we patch that? How do we make it larger? Well, and again, just to repeat, the issue is that the exposing point that I had before in the previous set, now over there, there's an inequality of the inequality that is tied here in this area will not have an exposing point in an orange exposing point. Okay. So what can I do? Well, I just remove those inequalities. That's the idea. You take all of these inequalities whose exposing point was lost by this shoving that you did, and then you just remove them. You just remove all of those inequalities. And this is what we write here. I don't want to, because I'm running a bit late, so I'm going to go a little bit faster. And what you get is this nice S-free set here, which you're actually making it a bit larger because you remove all of those inequalities from the description of the region, of the green region. And well, even though this is an outer description, we also were able to work out a closed form formula for this set. So now, the second question, the next question is the case distinction necessary? Did I use, the proof uses the difference between the norms, like which one is larger, but actually we can show with the simple example that this same idea doesn't work in the other case. So this is an illustration of the other case when the norm is greater than D, okay? You can just take my word for that. And then you have this set that we had before, the wedge. Now the idea that I just told you is remove any inequality that doesn't have an exposing point. So what this would mean in this case is that you keep this inequality in the bottom, but the one at the top, you remove it. Oh, and you end up with this set, which is too large. It's actually is no longer S-free. So we need to do something different. And what we did is the following. We noted that for any fixed y, the set that we have is convex. Okay, Once you fix this, the set, it's a slice of the set, and it's a convex slice of the set. So what we did is define the following function. For each one of these slices, so look here, put your attention into one of these black slices, we optimize in some direction, okay? We optimize in that direction, and that gives us certain red points here. And now define as your set everything that goes beyond that. Okay, so you maximize in that direction, you get this point, everything that is beyond that you define as your set. And in this case,
5 minutes.
Yeah. So so you define that set, and in this case you get this thing. You get this purple region, which is maximal S3, and it's nice. So I'm gonna skip through some of this part. We actually had to prove that this function is convex, that the set is convex. There's a lot of little details that you had to fill in because you need to make sure that what you're constructing is convex, is maximal, and whatnot. So we did that, and we actually were able to find a closed form solution of this function, which is not too bad. It's not the nicest, but it's also not too bad. Okay, it's at least closed form. And we prove that this is maximal S3, that this construction gives you maximal S3. I'm going to skip off what's the exposing point, but the exposing point is given by that maximization problem. So just to repeat here, what we have is that set, and with this new construction, you actually get the maximal S3 set. Okay, you do the tilting of the inequality instead of just removing it. Okay, so in the last few minutes, I'm going to give you the idea of how we deal with non-homogeneous quadratics. So we come back to the equality of this, of the equality form of this one hyperplane, okay? So instead of having the less or equal than 0, we go back to equal to 1. So again, we have to distinguish these two cases, depending on where the norm stands, so if the norm of A is greater or not. In the first case, in the easy case, the case where I just removed inequalities, remember? So in that case, maximality carries over to this other set. So that was nice. That was easy to obtain. So I'm not gonna talk too much about that. The other case is very interesting because in the other case, let's look at what happened. So this set is the maximal S3 set that I just described to you with this weird looking function. And now we have this orange set here, but now I'm slicing both things with a hyperplane. And if I project that, I get this thing here. And as you can see here, well, the set is not maximal anymore. You can just see it from this picture. However, it seems that the slopes are okay, and that if you were able to translate this a little bit more and towards the asymptote that is given by this line here, you should be okay. So what we did was follow exactly that strategy. It began as a conjecture, let's say, that you have this outer description of your set. So these are only all the valid inequalities. And then we prove that if you just relax some of the inequalities, you get a maximal S3 set for an adequate relaxation. So this R beta is something that we needed to compute. And how we computed that R beta is something that me and Felipe really liked, is the following idea. So we find a sequence of points moving along S, okay, that is approaching this desired inequality that is not tight. So this inequality here, that it's the one that's creating issues, you go through S and try to get as close as you can. That's the idea. And we actually formalize this as an extra layer of our maximality criterion, which is no longer an exposing point. We call this an exposing sequence at infinity, because it's approaching the inequality, but it never touches the inequality. Okay, so it's different than the exposing point. And with that, we were able to get a closed form solution for the R beta of this gap that we need, and we get actually the maximal S3 set. So just to show you, R beta looks like this, and we were able to prove that this gives you a maximal S3 set. And there's a very interesting fact here that we still don't fully understand. R beta happens to be the optimal dual solution of the optimization problem that defines phi, which was very surprising, in case someone is interested in those kind of things. And we were able also to get a closed form formula for this set, even though the construction of this relaxation that we did for this set uses the outer description of the set. We were able to get a closed form formula based on this same function that we defined before, this phi function that is optimization problem in slices of the set. Okay, so just to wrap up very quickly, as I mentioned throughout the talk, all our maximal quadratic-free sets have closed form expression. So this is good because when we compute the intersection cuts, which we're in the process of doing so, you can get the step lengths very easily because it's just a one-dimensional on this closed form. So it's, even though the closed form has some square roots, it's still nice. One thing that we're investigating now is how do this transformation of this canonical form that I mentioned when you diagonalize and homogenize, how does that affect the set? What I'm showing here is actually two different sets, two different maximal S3 sets, that the only difference between these two is that we took the quadratic and we diagonalized and homogenized in different ways. So we did it with two different recipes. We applied our machinery in both, and we got two completely different, well, they're not that different, but they're still different. So this is interesting because it means that the transformation is playing an important role on which maximal S3 set you get. And there's a lot of other questions. Well, we know for a fact that our construction doesn't yield all the maximal quadratic-free sets. We have some examples that we cannot achieve. And there are other questions like obtaining minimal representation of the sets. What happens if we include more linear inequalities, etc., etc. So that's all I wanted to say. Thank you for your attention. Thank you very much.
Great, thank you, Gonzalo. That was a fascinating talk. Let's hold the applause for after the questions. I think it's more efficient. So if anybody has a question, they could type it in or just say something in the chat, and then we can unmute you and you can ask your question. Giacomo has a question, I think.
Sorry, I can't raise the blue hand because co-host cannot. So you mentioned that the conditions for general convex sets, for general sets, it's only a sufficient condition, the one that, so can you give is there a simple counter example to the other direction? I mean, I'm sure there is, but is this something easy to see?
I wouldn't say it's simple. No. Unfortunately,
okay.
we have some construction. If you can ping me later, I can just actually draw it for you because it's not too easy to see. But we have some 2D examples where this fails. Yeah.
All right. Thank you.
Yeah.
Some other questions?
I think Robert raised a hand. Robert Hildebrand, I think I saw.
Hey, Gonzalo.
Hey, Robert.
Nice talk.
Thank you.
Is maximality necessary when you, like in the first picture, you had this kind of reverse convex set? And it seems like many of these S3 sets would give you the same inequalities.
Yeah, no. Normally, you don't really need to, but I don't think it's easy to determine when you don't need to. If you have a maximal S3 set, you know that you're going to dominate anything else that comes from another one, but it's not necessarily a strict domination. Okay, so it's like you play it safe with maximal, but you might get the same with non-maximal S3 set. Yeah.
Okay, thanks.
Great. Joe Pat has a question. You're unmuted.
Oh, thanks. Nice job, Gonzalo.
Thanks, Joe.
So going off of Giacomo's question, do you have some intuition at what might be a necessary condition, or what might you need to add to make this?
So we've pondered a lot about this, and we think that this condition that we have might be good enough for quadratics, for quadratic-free sets we have, because all the examples, the counter examples that we have for the condition are not quadratic sets. So we think that this might be enough for quadratics, but yeah, every time we try, I mean, we've tried a few months in separation of proving it, and we're not able to. So this idea of exposing an infinity we're still not able to handle it as in the other direction, essentially. Okay. I don't know if that, I hope that replied to your question.
Yeah. I'll ask some more later. Thanks.
Yeah.
Okay, I think we better stop and switch to the next talk. Let's thank Gonzalo. If everybody can unmute, then we can applaud.
Thank you. Much.